Welcome. Next, we are going to look at calculus of functions of several variables. For now, we will just look at the definitions. In differential calculus, for a single variable, we define limits and continuity and then look at the definition of the derivative. In some sense, our job is a bit easier because we are not going to do that much with limits and continuity. On the other hand, these concepts are important, even though they are much more difficult in the one variable case. Informal definition of limits is that we say that a function f approaches a limit L as xy approaches x0, y0, or the limit of f at x0, y0 is L if f of x, y is close to L whenever x is close to x0 and y is close to y0. And I can make f of x, y as close to L as I want by taking x sufficiently close to x0 and y sufficiently close to y0. What makes this difficult is that there are so many different ways in which x, y can approach x0, y0. They can approach at a uniform rate, but at differing rates. So if you think in terms of graphs, think of x0, y0 as a point in the xy plane, and you are approaching it. You can approach it in a straight line, or infinitely many directions. You can approach it in a spiral, or you can approach it in a stairway fashion. That is, first you move a little bit parallel to the x-axis, then parallel to the y-axis. So because of all this possible, it's a little bit harder to find limits. And we are going to be interested only in elementary functions. And for elementary functions, limit equals value. In some sense, more formally, we define continuity same way as we did in one dimension. A function is continuous if limit equals the value. In particular, the function should be defined at that point. And elementary functions are continuous wherever they are defined. You have to be a bit careful here. For a function to be continuous, it's not enough that it be defined at a given point x0, y0, but at all nearby points. The issue is this. If you take x to the power 1/3, that's fine. It's defined no matter what x is. But if you take x to the power y, then you have to be careful. X is negative. X power y is defined only if y is a rational number with an odd denominator. But if you take a nearby value of y, it may not even be a rational number, which means that we cannot define x power y, so we cannot really talk about the limit. Most of the time, this wouldn't really matter because in applications, these kinds of things don't happen, which means we are not going to worry too much about it. So let's get on to the main point of business, define derivatives. There are several different ways to generalize the concept of a derivative. We'll take the one which is conceptually the simplest in terms of calculation, doesn't require us to do anything new, but in some sense is limited. We'll talk about this when we talk about the chain rule and the differential approximation. For now, let me just concentrate on the calculational aspects. We define what's called the partial derivative of a function f with respect to a variable x by doing what we do in experimental sciences often when there is more than one variable. Change only one thing, trying to keep other things as fixed as possible. Of course, mathematics, ideally, you can keep things absolutely constant, which means that when I look at the derivative with respect to x, I keep every other variable constant. So if there are just two variables, I change x by some amount, don't let the other variable y change, then take the change in the function over the change in x. So in other words, I take f of x plus h comma y minus f of x comma y over h, and then take the limit as h goes to 0. Since there is only one variable that's changing here, this is really the old one variable limit, so even that's easy to calculate. And this is called the partial derivative in some sense because it tells us only part of the story. It tells us what happens if we change x without letting y change. Of course, the same way we can talk about partial derivative of f with respect to the second variable. We change only that variable, keeping x fixed. This also gives us a way of calculating these things. If you go back to the definition of the partial with respect to x, note that y doesn't change, which means I can treat y as a constant, pretend that f is a function of just a single variable x, and then we can apply the rules of differentiation from chapters 11 and 12. There's a point of notation here. Prime notation doesn't help because in prime notation we have to know with respect to which variable I'm differentiating. So instead of prime notation, we use subscripts, subscript being name of the variable with respect to which I differentiate. If I let x change and take the rate and then I denote it by f sub x, if I'm differentiating with respect to y, I denote it by f sub y. With the d notation, we use curly d to indicate that we're talking about partial derivatives. Otherwise, it looks just like one variable notation. I denote the partial derivative with respect to x as df over dx, the partial derivative with respect to y as df over dy. We can also give a geometric meaning to this. If f is a function of two variables, we can represent the graph as a surface. If you think of f as giving the elevation of a point on the surface, then you can think of df over dx as the rate at which the elevation increases as you go parallel to the x-axis. If you go parallel to the x-axis, y doesn't change, and the rate at which f changes is the rate at which the height changes. Same thing for y. Because there's nothing special about functions of two variables. We can do this for any number of variables. The idea is the same. You keep all variables except one fixed at the starting value, let only the remaining variable change, and then take the corresponding rate. Next time we will talk about calculating these.